So, good afternoon. My name is Chase Ammon, and before I get started, I thought it would be great to get to know you guys a little bit better. So, on the count of three, everyone could shout out their names. 1, 2, 3.
Lindsay.
Amazing to meet all of you. So, I will be presenting on the effects of canopy gaps on soil respiration, and I'm an RU student with the ISE project. So first I'm going to give you a background on respiration, and then I'm going to talk about my methods, my results, conclusion, discussion, and then a few concluding remarks. So most of you probably know this, but soil respiration is the combined carbon dioxide released when autotrophs and heterotrophs in the soil are respiring. And autotrophs make up about 20% of soil respiration, so that would include tree roots, things like that, whereas heterotrophs make up 80%. And we humans can have a huge impact on soil respiration by altering the factors that impact soil respiration, which are mainly temperature, moisture, nutrient content, and oxygen levels. So soil respiration is extremely important in the global carbon cycle. It's the second biggest contributor to the cycle after photosynthesis, so just a small interaction in this can have a drastic impact on global carbon levels. So that's why it's really important to understand what's happening here and to understand how humans impact this cycle. So for my experiment, I am a student with the ISE project, so I was incorporating that into my methods, but the ISE plots are designed in, there are 8 subplots in each ISE plot, so each of these little dots is a soil respiration collar, and they're randomly located within each of the 8 plots, each of the 8 subplots, and I used only the high treatment plots and the control plots just to have a more distinct canopy gap. And then for my plots, I have 8 plots around the valley, and I had soil collars, and each cardinal point, and then one in the center. So I was looking pretty much at the difference between natural gaps and anthropogenic gaps. So for natural gaps, I had the ice storm plots, and then I had 2 blowdown sites. And then for my anthropogenic gap, I had a clear cut that doesn't really look like this, but you'll see what it looks like in a second. So here's a map of my plot. So where this big red arrow is, these plots up here are my clear cuts, and these here are my blowdowns, and here are the ice plots. And you might be thinking these are located in such different places, there are different moisture levels, different elevations, but that's not really that important to my project because each site has a reference plot at it. So I was really looking at how they differ between their treatment plot and their reference plot. And so here is one of my clear cuts. As you can see, there's a big open field with a lot of a lot of shrub growth, and basically no canopy, just sky. And here's my soil collar. That's where I was taking my respiration measurements, and as you can see, there's a lot of plant growth and not a lot of decomposing material. This is just basically 100 meters away. This is its reference site. You can see thicker forest, hardly any sky, and then no undergrowth, a lot of decomposing material. So here's one of my blowdown sites. The canopy gap is less drastic, but there is still a significant gap here because of this light reaches the forest floor, which allows undergrowth to sprout up. So here we have ferns and hobble bush, and then here it's a little dark, but you can see the fallen tree there that caused this big gap. And here's its reference site. Again, a lot less undergrowth, more decomposing materials, no gap, thicker forest. And here's the ice plots. This is one of the 2 ice plots I was looking at. This is plot 9. So again, you can see a big gap, more light reaching the forest floor, which is causing more things to grow on the forest floor, and then there are all the fallen trees in its reference site. So kind of the same deal. So the measurements, I was using a Lycor, which is a little bit annoying, but it gave me all of these measurements here: humidity, temperature, soil moisture, soil respiration. So it was a really cool thing. And then I had a soil temperature probe as well, which gave me deeper soil temperature measurements. So temperature and soil respiration are directly related. I guess it's more of this is only from 15 to 25 degrees, so it doesn't show the whole curve, but it's more of a bell curve. So after about 35 degrees Celsius, soil respiration processes begin to slow down because it's too hot for the microorganisms, and And then obviously at lower temperatures it's too cold. But because it's just like whenever things are warming up, things are moving faster, they need more energy, so they're respiring more. And then with moisture, it's not quite as directly related. Moisture really only impacts respiration at extreme values, so at very low water content, these organisms do not have enough water to survive, and then at very high water contents there is not enough oxygen because it's too saturated with water. And for heterotrophs, there's a small increase as soil moisture increases, and for root respiration, there's a little bit more. So because of this, I expected kind of temperature to be more of the controlling factor than moisture. So because these gaps allow more light to reach the forest floor, I expected there to be higher soil temperatures. I thought there'd be lower moisture levels because there'd be more evaporation, and I expected there to be higher respiration because of the increased temperatures. And I thought that the impacts at our anthropogenic sites would be greater than at the natural ones because you see a lot more extreme gaps. So the goal of my project was, as climate change progresses, extreme weather events are forecasted to become more frequent and severe, leading to more gaps in forest canopies. So the goal is to study and understand how the effects of different canopy gaps impact forest soil processes. Sorry for reading that to you. So for my results, just keep in mind all of my gaps will be in blue, like the sky, and all of my references will be in red. So first I'm going to talk about temperature. As I said, I expected there to be higher temperature at my sites, and this is what I saw at all of my gaps. So here's topsoil temperature above at the clear cut. I should note that I took soil temperature and temperature right above the soil, and I'm just showing you this graph because I have more data and because I didn't have any of that for the ice storm at this point, but they did look exactly the same. So here's average topsoil temperature at the clear cuts. As you can see, about 5 degree higher temperature at the gaps. Less severe at the blowdown, but there actually are error bars on here. They're just so small you can't see it, so there is significant difference. And then here we are at the ice spots, more significant difference between the two. So that was really what I expected to see for soil temperature. And for moisture, I expected lower lower moisture at gaps. And that's not what I saw at all. At all of my plots, I saw higher moisture levels, which kind of surprised me at first. Then I learned about evapotranspiration from Joe Haley. And basically, because at these gaps, there aren't as many trees, and trees are a huge contributor to evapotranspiration. They take up so much water through their roots, and all of that is evaporated or transpired into the atmosphere. So here I'm seeing that transpiration is actually having more of an impact than the evaporation. And then for respiration, I expected higher respiration at gaps, and guess what I did not get? I actually got higher respiration at all my reference sites, and this confused me because I had higher temperatures at all of my gaps, so I thought respiration and the temperature are directly related. Why aren't these mirroring each other? This is at the blowdown, and then this is at the ice storm plot. And if you look at the linear regression, you see that curve where it's increasing, and then as it gets too hot, the respiration is starting to slow down a bit. And obviously that's like a really crappy R-squared value, but you can at least see there's some trend here. And so here's moisture and soil respiration regression. Again, there's almost no trend here, so I didn't really read that much into this. But if temperature is increasing, why wasn't respiration? That was a big question that I had. And my first idea was maybe my soil moisture measurements were wrong. At the beginning of the summer, the LICOR had really, really wacky temperature measurements, and I only had measurements from the second half of the summer. And I actually had humidity measurements for the whole summer, and they were showing me the opposite of my moisture level. So I thought, and it's taking humidity like right at the soil level. So I expected that soil moisture would have an impact on the humidity right above the soil. And that was doing pretty much exactly what I expected. At the reference site, there was higher moisture levels at the blowdown site, at the reference site, there was higher moisture levels, and at the ice plot, there was higher, at the reference plot, there were higher humidity levels. So this is something that I'm a little confused about because I don't really understand why moisture and humidity would be doing the opposite thing. But then when you look at humidity and soil respiration, you see that trend that you'd expect with moisture. And then when you look at air temperature and humidity, you also see the same trend you would expect as temperature is going up. The relative humidity was going down. So this is just a little bit confusing. And then I did the same thing with the moisture and it's showing the opposite thing. So I think maybe my data might be a little wacky right here. And so I also thought another reason for the difference, for the reason that I saw higher respiration at my reference sites and at my gaps could be just a lack of basically food for these microbes. So as you can see, there's so much more decomposing material here than here, and I just thought carbon availability could be the limiting process for respiration, especially because microbes account for so much more of the respiration in soil respiration. And then another thought is nitrogen. I didn't look at nitrogen at all, but with more nitrogen you have higher plant growth rates, and more growth means you need more respiration. So all the woody debris that's falling at these gaps is sucking up all the nitrogen. So maybe you're having more plant growth at these reference sites and needing more respiration for that. So I'd have to measure nitrogen to give you the right answer to that. But I do have a few conclusions. My first is that canopy gaps cause warmer soils, which I expected, and I'm glad that at least that worked out. Canopy gaps reduce transpiration rates, which increase soil moisture. That's kind of a question mark because my moisture data is a little wacky. Soil temperature and moisture did not account for decreased respiration at canopy gaps, so that means something else must be, maybe it's higher nitrogen levels, maybe it's fewer roots or decaying material. And then finally, anthropogenic disturbances have a greater impact on these processes. And you saw that carbon dioxide release was higher at the gap sites. I'm not saying that we should go and clear cut everything, so that just must mean that carbon is being released in other ways when we're foresting or clear cutting. So there are a lot of things I would do differently. I would start earlier. My light core, we were sharing with 3 other people doing their research, so I had it on and off. I'd have it for like 1 week, and then 3 weeks I wouldn't have it, then 2 weeks I would, and then it was kind of a mess. I would also use a handheld moisture probe just so I could get that consistent moisture data throughout the year. I look at nitrogen, soil oxygen levels, and decomposition levels because those are all things that impact respiration. So I just want to have a few acknowledgements here. Dr. Rustick, Dr. Campbell, Big Gabe, which is this Gabe, and Little Gabe, which is and